So in chapter 14, we are going to continue our study of the ocean. In this chapter, we're going to take a look at the composition of ocean water and the different properties. And then we'll take a look at how the salinity and temperature and density of water affect the living organisms and basically divide the ocean into zones where different organisms can live. So the first thing that we have to consider when we look at ocean water is, what is it made of? Well, of course, it's mostly water. We can see that here. Mostly water. And then the salts, which are of various composition, primarily sodium chloride, but other salts in there too, make up about 35 grams out of every 1,000 grams of ocean water. And so we say that there's 35 parts per thousand. Okay, so it's not 35%. You notice this kind of strange marking down here, this 0/00. That means per thousand. So 35 parts per thousand of salt, and the rest is water. So now we're going to take a closer look at this with the Smart Figure video and look at how temperature and salinity change depending on where we are in the ocean.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe some of the components of ocean salinity and describe how salinity varies over the face of the world ocean. Here's a look at the barrier islands of North Carolina's Outer Banks. This is a place that I used to go on vacation when I was a child to go and play in the ocean, and one of my earliest memories is of the very different taste of ocean water compared to the fresh water I was used to swimming in back home. What makes ocean water salty? Well, most of ocean water is in fact water, and there's only a very small portion of ocean water which is salt, and that's represented on this pie chart with a little gray wedge. If you take a look at those dissolved constituents, you can break them out, and we can label each of these different pieces of the pie. So water makes up the bulk, obviously, of the ocean. Seawater's salinity is 35 per mil, so that's parts per thousand rather than parts per hundred. And that salinity is coming from dissolved salts. Most of those dissolved salts are chlorine, so that's this big wedge over here that's colored green. The second most common salt is sodium. And then you can see there's also smaller proportions of things like sulfate, magnesium, calcium, potassium, and then minor constituents. There's a little bit of just about everything dissolved in seawater. Now let's go ahead and take a look at how salinity, in other words the concentration of salts in ocean water, how that varies over latitude. So let's slice down through the world's oceans from North Pole to South Pole and look at variations in salinity and temperature over that distance. So that's what this graph refers to. So this is a chart showing latitude on the horizontal axis. You can see the equator is right there in the middle, and then the North Pole is over on the left, and the South Pole is over on the right. You can see that temperature follows a pretty predictable path over this range of latitudes. So obviously temperature is greatest near the equator where the sun is most directly intersecting the Earth's surface, and then temperature is least towards the poles where the sunlight is coming in at a glancing angle, and so there's less warming from the sun's energy. Now you might expect the salinity graph to have a similar sort of appearance, but it may surprise you to learn that it actually has two peaks.
So you'll see here that salinity doesn't follow temperature. We have kind of a dip here in the middle, close to the equator, and then these peaks as we get to between 20 and 30, 40 degrees north and south latitude. And then we really drop off towards the North Pole, and then somewhat of a drop over here at the South Pole. So what accounts for this difference, and why do we have these two peaks here? Well, a lot of it has to do with the atmosphere and how we get wind currents, and how wind, as it flows across the ocean and as these clouds flow across the ocean, they essentially pick up moisture. So if we look right here at this trough, right in the middle, right around the equator, why does salinity drop here? Well, salinity drops here because at the equator, where we have a lot of convection from the sun, we have a lot of clouds, we get a lot of rainfall. And as we add that tremendous amount of rainfall to the ocean, it essentially waters it down. Rain is fresh water. So it detracts some of that salinity out, and so it drops a few parts per thousand. As we look at what's happening here around 20 to 30 degrees north and south latitude, at this point, now we're away from the equator and we're in an area where we don't have as much rainfall. If we were looking at the terrestrial environment here, we would see that these would be deserts. But over the ocean, we're going to not have as much fresh water. So the salinity is going to increase there a little bit because we don't have that rainfall that is basically taking away some of the salinity. Then if we look at the North Pole and the South Pole, we've got a couple of different things that are happening here. Of course, we have snowfall, right? And then we have the melting of icebergs and sea ice. So as the icebergs and as sea ice melts, this is going to add a large amount of fresh water to the seawater and again, decreasing the salinity. And this pattern is essentially seasonal. We're going to see a lot larger seasonal fluctuations in salinity at the North and South Pole as we get the melting and formation of the ice caps than we do here at the equator and the middle latitudes. Something else that we have to consider in addition to salinity is acidity. When we burn fossil fuels and release carbon dioxide into the atmosphere, it can rain back down and get into the ocean and form carbonic acid. And this is going to lower the pH of the ocean, which can really interfere with the food chains and the food webs and the overall productivity of the ocean. So we'll watch another smart figure video here that discusses the pH scale.
Hi everybody, it's Laura Faye Tenenbaum, and in this smart figure, we're going to look at the pH scale, including pH values of some common substances. Now, pH stands for power of hydrogen, and the pH scale is a measure of the concentration of hydrogen ions in a solution. The pH scale ranges from 0 to 14 and measures how acidic or how alkaline a solution is, with 7 being neutral, which is neither basic or acidic. And anything from below 7 down to 0 is increasingly acidic, meaning that it releases hydrogen ions when dissolved in water, and everything above 7 all the way up to 14 is increasingly basic or alkaline, meaning that it releases hydroxide ions when dissolved in water. And for a pH of 7, which is neutral, it means that hydrogen ions and hydroxide ions are found in equal concentrations, so we call that a neutral solution. The other thing to remember about the pH scale is that it's logarithmic. And what that means is that a 1 unit change in pH actually represents a 10-fold change in the hydrogen ion concentration. So for example, a pH of 5 is 10 times more acidic than a pH of 6, and a pH of 4 is 100 times more acidic than a pH of 6. Now on this scale, you can see that pure water is neutral at a pH of 7. You'll also notice that seawater is slightly alkaline with a pH of 8.1. And you'll see that seawater, blood, and eggs all have about the same pH. I know that kind of sounds disgusting when you think of eggs and seawater and blood all together, but the interesting thing is that if life did indeed evolve from the sea, as is theorized from the fossil record, then you would expect that the fluids associated with life, like eggs and blood, have a similar pH as the seawater, and that's kind of amazing. So now let's go up the scale and check out some of the different substances that you might be familiar with as examples. You've got bleach, antacids, and baking soda, which are more alkaline than the seawater, and milk of magnesia is even more basic or alkaline. then ammonia, and then drain cleaner, and then oven cleaner, and finally sodium hydroxide, which is also sometimes called lye. Sodium hydroxide or lye is used to cure some types of food like olives, and it's also used in making soap and other household cleansers. And you can see, as you go up the scale to the right on this figure, the substances become more and more alkaline and also more and more corrosive and toxic. And of course, you probably have some of these high pH items around your house. For example, go check out the safety warnings on a can of oven cleaner. Now let's go back to the pure water, the neutral substance with a pH of 7, and check out the examples on the acidic side of the figure. You've got milk as slightly more acidic than water, and then unpolluted rainwater is even slightly more acidic than that, and then beer and coffee are even more acidic, and then over to tomatoes, grapes, vinegar, soft drinks, and wine, even more acidic, lemons and limes. You're probably more familiar with these acids, and as you know, when you eat some of these items, the acidity can make your mouth tingle a bit. Stomach acid and then battery acid are examples of extremely acidic types of substances, both of which can be very corrosive as well. So I hope this smart figure helps you understand the concepts of neutral, alkaline, and acidic, and gives you some idea of these common and familiar things that you might have seen around your home to put these concepts of pH values in context with something that you already know.
So there we got a little bit of information about the pH scale, and so you can see that affecting the pH of ocean water can really wreak havoc on all of the ocean ecosystems. So we're going to switch gears now and look at variations in temperature and density as we move in depth throughout the ocean, and I'll interject periodically with more information.
Hello there. Welcome back for another Smart Figure. This is Callan Bentley. After watching this video, you should be able to describe the vertical structure of the oceans, including the thermocline and a related concept, the pycnocline. We've already learned that temperature varies fairly systematically over the face of Earth's oceans. This is surface temperature of the oceans, where we're looking at variation in latitude. So basically, here's the North Pole over on the left and the South Pole over on the right. And at the equator, you can see that the ocean temperature is at its warmest. But how does that change when you go to greater and greater depths in the world's ocean? Let's take a look at how temperature varies in two different circumstances, low latitudes and high latitudes. Let's begin with the graph on the left, low latitudes. If we draw the temperature profile for a low latitude ocean, we see that it's very warm near the surface and that it's relatively cold at greater depths. And there's this zone in between where there's really rapid temperature change with depth. That's called the thermocline. All right, that zone of rapid temperature change with depth is called the thermocline. At high latitudes, however, we see that there is no thermocline, that basically the water is cold at the surface and it is cold at depth. So the thermocline is absent there because the water temperature is pretty much the same all the way down.
When we have the absence of the thermocline there, that is called isothermal, in that the water is roughly the same temperature all the way throughout. Now we contrast here low latitudes and high latitudes. What happens in the middle latitudes, like where we are? Well, mid-latitude waters have kind of an intermediate pattern between the two. During the summer, there's a strong thermocline that's present. And during the winter, as the sun is not at as high of an angle, then the temperature starts to drop and the thermocline goes away, and it more so resembles what we see at high latitudes.
We're going to consider density now. This is how dense the water is, and this varies based on how warm the water is and also how much salt it has dissolved in it.
So what is density? Density, you see there the unit is grams per cubic centimeter. So what is density? Well, it's the mass per unit volume. In other words, it's how heavy is something for its size, okay? And we talked a little bit about this when we looked at our minerals, that we had something like galena that was very dense. It was very heavy for its size. And the temperature of the water, as well as the salinity of the water, can affect density.
What we see is that low latitudes, a very similar looking picture where if we draw the density, it is least dense up near the surface. Then there's a zone of rapid density change, which is called the pycnocline, and then it's relatively constant at depths that are greater than about 1 kilometer. At high latitudes, once again, there is no real variation. Basically, it's about the same density all the way down from the surface to the bottom of the seafloor. If you look at a total cross-section through a hypothetical ocean basin that stretches from 60 degrees north to 60 degrees south, you would see that there is this layering to the world ocean where you have this surface mixed zone and then this transition zone where the thermocline and the pycnocline are being crossed. And then most of the world ocean is the deep zone, which is shown on this graphic in the color purple. You can see here that the stratification of the world ocean is at a minimum over towards the polar regions. Okay, let's go ahead and test you now. What would you expect to find in terms of layering in the ocean, both in terms of temperature and density, if I kidnapped you and took you in an airplane and then dropped you off at a place where this is what you saw? All right, so you're looking out the airplane window and you're looking out over sea ice. So you've got a lot of sea ice here. What would you expect in terms of ocean stratification at this location? Well, hopefully you figured out that sea ice is likeliest to occur near the polar regions where it is relatively cold, relatively high latitudes, and so therefore you'd expect to see an unstratified ocean at these locations. So there would be no pycnocline and there would be no thermocline. Hopefully you got that, and I'll go ahead and unkidnap you now and return you to your video screen.
So now we have a look at how salinity, temperature, and density vary throughout the ocean. So we'll look now at how that affects the living organisms. So the ocean is very diverse. We have on Earth about 2.3 million species, and of those, we have about 10% that are going to live in the ocean. And we're discovering more and more every day as we explore the ocean more and get deeper and deeper into the ocean. We're discovering animals that we never knew existed. Most of the marine organisms, though, live within the sunlight. So they live on the surface. They live up close to the surface of the ocean. Because a lot of these organisms are going to perform photosynthesis. They need the sunlight in order to make sugars, make food, and then those organisms are going to be eaten by other organisms and eaten by other organisms and so on to develop our food chains and our food webs that we have within the ocean. So because these organisms that are performing photosynthesis that form the bottom of our food chains and food webs live up closest to the surface, well, then a lot of the other organisms are going to live up close to the surface too, so that they have access to this ready-made food, essentially. So when we look at the organisms that live in these marine environments, one advantage is that, there's plenty of water available, which all organisms need, but maneuvering in water can be kind of difficult in some cases. So the success of these organisms depends on their ability to be able to evade predators, find food, and then cope with the challenges that come with living in, a sometimes turbulent environment. So when we look at our different marine organisms, we can classify them in several different ways: where they live, how they move. And so we're going to look at three groups of marine organisms. We have plankton, and we can divide this into the phytoplankton and the zooplankton. We have nekton, which are the swimmers, and then we have the benthos, which are the bottom dwellers. So we'll watch another smart figure now to learn more about each one of these groups.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. This time we're going to take a dive in the ocean and classify some of the different forms of life we find down there. So first off, there's the floating forms of life. Many of these are small, some of them are larger, but basically if an organism is a floater, We call it plankton. Plankton can be phytoplankton like you see in this image. It could be zooplankton like you see in this image. Even something as big as a really big jellyfish would be considered plankton if it floats.
So going back and talking a little bit there about phytoplankton versus zooplankton. Phytoplankton are essentially algae. They are photosynthetic. They're going to absorb sunlight and make food. Zooplankton are more like animals in that they're going to have to feed off of other organisms. So essentially your phytoplankton form the base of your food chain or food web, and then the zooplankton are going to feed on the phytoplankton.
On the other hand, sharks don't float. Instead, they swim. And that's true for fish in general, and even things like this squid. So we have a different term that we apply to all those organisms which are swimmers rather than floaters. Collectively, we refer to them as nekton. Here's another example of nekton. This would be a mammal example of nekton, and that's, of course, a whale.
Nekton are also limited to certain environments in the ocean. The temperature, salinity, density, and availability of nutrients limit their range. And so we'll see a lot of times that these organisms live up closer to the surface too, because they're going to feed on the phytoplankton or the zooplankton.
Well, what about this guy? This is a sea star. It doesn't float. It doesn't swim. It crawls around on the bottom instead. Here's a crab. Again, sort of a bottom crawler, although capable at moments of sort of jetting through the water. Organisms that live on the bottom are referred to as benthos. So the benthos are the organisms that are on or in the bottom. This sponge would be an example of benthos. This is benthic epifauna, meaning that it lives on the bottom. This is, of course, a sessile organism, meaning that it doesn't move around in the same way that a crab does, but it's anchored to the bottom. A worm would be an example of benthic infauna, something that lives in the sediment. All right, let's quiz you now. Say the copepod up here at the top. This is a crustacean. It's an animal. It needs to eat. So what would that be? Hopefully you said plankton, and you said that that would be zooplankton because it is not making its own food with sunlight. It's having to eat instead. And another one here to quiz you. This is a sea urchin. You can see that it's moving around with its little tube feet on the bottom. And because we're talking about the bottom here, we're probably talking about benthos. Hopefully you got those two correct. Pretty.
So another thing about these benthic organisms, and you can kind of see around here that because these benthic organisms live on the bottom of the ocean, it's always dark. The sunlight can't reach that far. And they must feed pretty much on each other, or whatever nutrients do fall from below, which we know may take a little while. So it's very cold, it's very still, and it's very dark as we consider the bottom of the ocean. So using the availability of light and some other factors, we're going to divide the zones of the ocean into different areas. So how do we do this? Well, first of all, like I mentioned, availability of light. Okay, so the amount of light that's available is going to determine what animals can survive in a particular area. We also have to look at how far away are they from the shore? Are they close up, or are we talking about, deep ocean? And that also goes along with the water depth. So if we take a look at this figure, this is figure 14.13, which is on page 440. And you can see all of these different zones that are going to be represented here. So here's sunlight coming in. You see the limit of sunlight penetration here. And so if we're looking at available sunlight, this is going to be called the photic zone. Photo meaning light, ic pertaining to. So this is going to be the photic zone. Now, if we look below the photic zone, where sunlight is not able to penetrate, this is called the aphotic zone. A meaning without. So that's the aphotic zone. But we have this little bitty subdivision here, Okay, you notice it says euphotic zone. Eu means true. So this is really the best area for photosynthesis to take place. This is going to be where light is very strong, and we're going to see our greatest concentrations here of our phytoplankton in our zooplankton, because this is where the photosynthesis is occurring at the highest rates. Okay. Down here in the aphotic zone, we have no photosynthesis because light can't reach that far. Now, if we look at the distance from shore, okay, so our first zone we have is the intertidal zone. This is this narrow little strip of land right here between the high and low tides. And so this can be a harsh place to live because you've got this constant influx of water, coming in and out, crashing waves. It dries out from time to time, and you have rapid changes in temperature and salinity. But we do have a lot of organisms that live in these intertidal zones and really flourish there. The next zone that kind of lies right on top of the continental shelf is referred to as the neritic zone. And it's going to be from the continental shelf until we get to that shelf break and the continental slope. Most of the time it's going to be shallow enough for sunlight to reach there. So it's typically within the photic zone. It is rich in biomass and also the number of species that live there. Now, beyond that, once we get to the continental slope and beyond, that's referred to the oceanic zone. Of course, this would be the open ocean. We're not going to see as much nutrients here. Now, the third way we consider this is with the depth. So the pelagic zone is this kind of top area, really the open ocean. This is where you have the animals that are going to be floating or freely swimming around. The phytoplankton, zooplankton, nekton are all going to be here. And then we have the benthic zone, which is on the bottom, regardless of where you are. It's just anywhere on the bottom. And then eventually we kind of get to this abyssal zone, which is on those abyssal plains, which are the deeper parts of the ocean, where it's very dark, very cold, very high pressure. Organisms have to be very specialized to live in those areas. So now that we've taken a look at the zones where we find the different animals that live in the ocean, now we can look at productivity. So some regions of the ocean, of course, teeming with life. Other areas are completely barren. And this is related to what we refer to as primary productivity. Primary productivity is referred to as the rate at which organisms store energy through the formation of organic matter, using energy derived from either the sun or from chemical reactions. So how much carbon, essentially how much matter, is something going to be able to make due to either photosynthesis or chemosynthesis. This is influenced by how much solar radiation we have, because that influences photosynthesis, and then the availability of nutrients. All of those other organisms besides phytoplankton that can't make their own energy, that they're dependent upon others for their food so that they can perform chemical reactions, the availability of nutrients is going to really affect how much productivity we have. So we're going to take a look at another smart figure that looks at productivity in various areas of the ocean.
Hi there, folks. This is Callan Bentley, and you're back for another smart figure. In this video, we're going to take a look at changes in productivity of the oceans over the course of the year. So we're going to be taking a look at the relationship between phytoplankton and zooplankton, as well as the sun and ocean nutrients. Phytoplankton are the small, generally, we've got a human hair here for scale, small little organisms that live in the ocean. They're floaters, so all plankton float. And we're looking at coccolithophores, which are the organisms that make up chalk, diatoms, which have shells that are made out of silica, and also dinoflagellates. What all these diverse organisms have in common is that they're capable of photosynthesis. They're capable of capturing some of the energy from sunlight and using that energy to bind together carbon dioxide and water and use that as a source of energy. Phytoplankton are eaten by zooplankton. Zooplankton are the floating animals and foraminifera, radiolarians, and things like that. Basically organisms that need to eat. So these are not capable of photosynthesis, and instead they're going to consume phytoplankton or they're going to consume other zooplankton. So let's take a look at a pretty simple little scenario here. This is an example from the Barents Sea, which starts to get more sunlight in the spring. And you can see that sunlight results in an increase in the number of diatoms. So the overall diatom mass goes up. Diatoms are an example of phytoplankton. And then as soon as there's more phytoplankton to eat, you can see that there's a lag, but then there's an increase in the number of zooplankton too. So as they're eating the diatoms, basically they're playing catch up. And we reach a peak of diatoms in approximately May. The zooplankton haven't reached their peak yet. But you can see that as they consume more and more of the diatoms, we start to see a deficit in the number of diatoms, and the number of zooplankton catches up. But now basically they're eating themselves out of house and home, and you can see that there's this big discrepancy here between the number of diatoms and the zooplankton that are consuming them, and the zooplankton numbers go down as well. Now let's look at a more complicated situation here. This is one for the temperate latitudes, where we've got several different curves here showing the increase in various proportions over the course of the year. So sunlight is the first thing. So you can see that basically there's more sunlight in the summer and less sunlight in the winter. And then we're going to take a look at the relationship between phytoplankton, nutrients in the water, and zooplankton. Now, a key thing to recognize here is that there are multiple variables that are interacting here to produce the shapes that you see on these curves. And one of the important variables is the thermocline. So the thermocline is the boundary that separates basically the warm, nutrient-poor water that's in the upper part of the ocean, where the sunlight is, from the cold and nutrient-rich water that's deeper in the ocean. During certain times of the year where basically we shift from winter into summer or summer back into winter, in the spring and in the fall, the thermocline can be upset, and then we end up getting mixing of the ocean. And so basically nutrients are brought to the surface where the sunlight is, and the combination of those nutrients and the sunlight helps spur the growth of phytoplankton. That's what we're looking at here. There's this big obvious spike in phytoplankton that occurs in the spring, and essentially that is due to the mixing of that nutrient-rich water from the deep with the surface water. So sunlight goes up, it gets up higher, the thermocline breaks down, the nutrient-rich water is brought up from the depths, and then the phytoplankton go to town on it, and they have a big population boom. And this big population boom is called a plankton bloom, B-L-O-O-M. After the phytoplankton consume the available nutrients, their population crashes. So in this case, the ingredient that's basically holding this whole system back is the number of nutrients. Once the nutrients are gone, the phytoplankton can't keep up, and their numbers stay low for the rest of the summer. Meanwhile, the zooplankton are having some food. They have a little peak early on in April and May, but then their numbers gradually decline and decline and decline throughout the rest of the summer as well. In late summer and into the fall, the amount of sunlight goes down, and so that encourages the breakdown of that deep thermocline and the establishment of a new shallower thermocline. And once again, you get mixing of the nutrient-rich waters from the deep, so the nutrients go up, and you can see that that's that red line taking the step up there. The nutrients are consumed by the phytoplankton, and they have a smaller bloom that takes place in the fall. Not quite as large as their spring bloom, but still a nice little blip on the graph. Now, a question would be, what would you expect for the response of the zooplankton to that fall bloom in the phytoplankton? Well, hopefully you said that if there's more food to eat, the zooplankton are going to eat it, and indeed they do, and you see there's another bump in their population curve. Again, it is commensurate with the size of the bump in the phytoplankton curve, so it's a smaller bump in the fall and a bigger one in the spring.
So the last thing that we're going to consider here is the relationships in feeding. So we've talked a little bit about this, about how the zooplankton feed on the phytoplankton, but we also have some plants that we'll have in the ocean. We have bacteria, we have some structures that are these organisms that are like bacteria called archaea. So these are our producers, and they're going to essentially provide all of the energy that is contained within these systems and within these relationships. So we're going to watch one last smart figure video that looks at how energy changes as we go throughout these, what are referred to as trophic levels in these feeding relationships.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. This time we're going to take a look at the flow of energy through a marine ecosystem and make an assessment of how efficient that flow is. So we've already talked about the different trophic levels that can be found in a marine ecosystem, which starts with the phytoplankton, those very small little floating organisms that are photosynthetic. They capture some of the sun's energy and turn it into biomass. And then those phytoplankton are eaten by the zooplankton, and the zooplankton capture some but not all the phytoplankton's energy. And then those are eaten by the various other organisms in the ocean, and of course then some of those eat the other ones. So the zooplankton are eaten by the small fish, and then the small fish are eaten by the medium fish, which are eaten by the big fish. Eventually you end up at the highest trophic level, these sort of apex predators, and humans are one of those apex predators. So let's take a look at an example here of that entire chain of energy transfer. The sun shines on the ocean surface. Let's say that it puts out 500,000 units of energy. And some of that energy is captured by the phytoplankton, but they don't capture all of it. They capture only about 10,000 units of energy. So that is a 2% efficiency. That 10,000 is 2% of the 500,000 we started with, which means 98% of that energy was not captured. Now it gets a little more efficient at this point because of that 2% that's captured, about 10% of it makes it to the next trophic level, the zooplankton, which means there's only a 90% loss there. And that same pattern holds true when we go up to trophic level 3, about a 10% efficiency, and then another 10% we go up to trophic level 4. And then with the apex consumer, trophic level 5, we see that we have another 10% efficiency and again a 90% loss. So most of the energy in the ecosystem never gets transferred up.
So what we're looking at here as we go through these trophic levels is you see we receive 500,000 units of radiant energy. But by the time we make it through our food chain and we get up to trophic level 5, the human or the apex predator, 1 unit is left. Okay. We lose 98% here and then 90% with each step. So for those initial 500,000 units, 1 unit is transferred to humans. So you can see that as we move through these trophic levels, the transfer efficiency really isn't very high. We're not able to keep a lot of that energy to use to convert to our cells usable form of energy. So when we put all of these different trophic levels together, we come up with either a food chain or a food web. A food chain is shown here for you on the left, where we have diatoms, which are eaten, which are phytoplankton, eaten by a particular type of copepod, which is a type of zooplankton, and then eaten by a particular fish, the Newfoundland herring. In a food chain, if this particular copepod, this Calanus copepod, if something was to happen to it and it was no longer available, the Newfoundland herring would have trouble because now there's nothing for them to eat. And our populations of the Newfoundland herring would decrease. But over here, this is the North Sea herring food web. And it is not as specific. You see, we have diatoms and dinoflagellates, and we do still have the Calanus copepod here. But we also have all of these other directions. So if the Calanus copepod was to die out or go extinct, the North Sea herring could still eat arrowworms or sand eels or tunicates or amphipods or euphasids. So it would still have a source of food. So food chains are less idealistic because if you have a break in the chain, then it causes problems everywhere else further down the chain. But in a food web, it's much more efficient if the food sources are diversified. So that brings us to the end of chapter 14. We'll have one more chapter that we'll consider with the ocean, and that will be chapter 15.